If we're going to use matrices to perform Gauss-Jordan elimination, we need to be able to recognize when the matrix is telling us something about the system. We know how to read the solution of the system from the matrix, but remember that sometimes a system of equations doesn't have a solution. For example, the system we're looking at here does not have a solution, because the two lines that are described by these two equations, if we graph them, we can see they're actually parallel lines. These never intersect. Because they don't intersect, they don't have any points in common, there's no solution for that system of equations. So how would we be able to tell that from Gauss-Jordan elimination if we just start working on the system in the form of matrices? Well, when we start by interpreting the system as a matrix and then perform elimination, if we, for example, use the RREF feature on our calculator, what we're going to see is the left side does not become an identity matrix. It becomes something else. And that's our first clue that something's wrong. If the system doesn't have a solution, then it's impossible to make the left side look like an identity matrix. Instead, this is the closest we can get. And if you read what the second row here says, it seems to be saying that 0x plus 0y equals 1. But the left side of that simplifies to just 0. So 0 is equal to 1, which of course doesn't make any sense. That's impossible. This is a contradiction, and we recognize that contradiction is telling us that the system of equations has no solution. So this is what you're going to typically see. When the system does not have a solution, there'll be a row in the reduced matrix after performing Gauss-Jordan elimination. There'll be a row that's saying something impossible, like 0 equals 1. Another possibility, instead of failing to have a solution, is that it might have lots of solutions. And for a system of linear equations, if there's more than one solution, there are actually infinitely many solutions. Here's an example where that happens. We have a system of 3 equations with 3 unknowns. And if we write that in matrix form and then perform Gauss-Jordan elimination, again, we did not get the left side to look like an identity, which is a clue that something is wrong. But it's a different issue than before, because when we looked in the previous example, we had something that didn't make any sense, a row that said 0 is equal to 1. Now that's not the case here. Now we have a row that says 0 is equal to 0. And that's fine. 0 is equal to 0. That's not a contradiction. What's going on is the first row of the matrix, after we've reduced it, says x plus y plus z equals 4. The second row says 1y plus 1/2 z equals 3. And the third row doesn't tell us anything. Now, if we found a single solution, we would expect that third row to be telling us what z is. But because there's a 0 coefficient here instead of a non-zero coefficient for the coefficient of z, this is not an equation that can tell us what z is. In fact, z can be anything. Z can be anything, which means there are infinitely many solutions. So if you pick a value of z, you can plug it into this equation to get a value of y, and this equation to get a value of x, in order to find a solution. Any z you want plugged into these two equations will give you a y and an x, which all together are a solution. Now, I'm simplifying the equations here. So this is y plus 1/2 z equals 3. I'm isolating y, so y is 3 minus 1/2 z. And then in this equation, I'm isolating x, and where there was a y, I'm replacing it with this expression that tells us the value of y. That's where this came from. And if you simplify all that, you get x equals 1 plus 1/2 z. So in summary, z can be anything, And if you pick a value of z and plug it into these two equations, you end up with a value of y and a value of x, and together the z you started with and the corresponding values of y and x are a solution. Since z can be anything, there are infinitely many solutions.